Today we are going to talk about forces. And so the first thing that we need to know about forces, what exactly is a force? Pressure?
No.
Any ideas what is a force? Nobody knows what a force is. Yeah.
Is it like, when,
What-
I don't know how to describe it without using the word force.
Oh, okay.
Pressure is like applying something like pushing.
So pushing, okay. And outside something or other, right? Well, here's a simple definition of a force. See if it makes sense. A force is an interaction between two objects that results in a push or a pull. If we think about the example of the dry ice demo, when my hand interacts with the dry ice block, resulting in a push, we would say there's a force there. Does that make sense? When I put the spring scale on the dry ice block and I pulled on it, there's an interaction between the spring scale and the dry ice block that results in a pull. There's a force present. So a force is an interaction between two objects that results in a push or a pull. That's what a force is. There are two types of forces. Forces are either contact forces or long-range forces. A contact force is where the two objects that interact are in direct contact. There's touching. For example, when my hand pushed on the dry ice block, while there's contact, while I'm actually pushing, when my hand is not touching the dry ice block, am I still pushing it? No. Okay, so that's contact force. Long-range force, the two objects interact at a distance. They do not touch, and yet still there's a force.
Like magnets?
Like magnets, right. Magnets don't have to touch in order for there to be a magnetic force, so that would be long range. So some examples of contact forces, there's some common examples, and some of these you may be familiar with, some of them you're probably not. The first one is friction. And notice the notation that we use for force, we use a capital F for force, and then a lowercase little subscript there. So FF is the force of friction. Friction is a contact force between a surface and an object that is parallel to the surface and resists motion. Does that make sense with what you understood about friction? Because you've heard of friction before. So it's parallel to a surface and resisting motion. For example, when I take my stapler on the desk and I give it a push, it doesn't move like the dry ice. Why? There's friction. So the stapler is moving what direction? Was moving to the right, and it was slowing down. So friction must be opposing the motion, and friction would be pushing to the left because it's opposing the motion of the stapler. The next one you probably are unfamiliar with. It's called a normal force, F sub n. The normal force is a contact force between a surface and an object that is perpendicular to the surface. In fact, in mathematics, the word normal means perpendicular. So normal force is just another way of saying perpendicular force. So when an object is in contact with the surface, there may be a normal force, a perpendicular force, perpendicular to the surface. The next one is called a tension force. Tension, Ft, is a force along a string or a rope. And a tension force is always a pulling force, and it's in the direction of the string or the rope. Now there are contact forces that don't fit into these categories, and whenever we see those, we simply refer to those as an applied force. You can call an applied force Fp for a pushing or a pulling force, or you can just call it F, some applied force. And so if there's a force applied by some object like a person that doesn't fall into these categories, we call that an applied force. For example, when my hand was pushing on the dry ice block, that's an applied force. I was applying a force to it, and it was a contact force. Any question about contact forces? Long-range forces include the gravitational force, Fg. It's a long-range force of attraction between two objects that have mass. Gravitational force, remember, I don't have to be touching the Earth in order to feel the gravitational force of the Earth. Okay, so it's a long-range force. And as we mentioned, magnetic force is another one. And another common long-range force is the electric force. Okay, these long-range forces you don't have to be touching in order to experience the force. For our purposes in this unit, we're only going to be considering the gravitational force as long-range. We're not going to deal with electric or magnetic forces at this point in the year. So for what we're doing now, force of gravity is going to be the only long-range force. And if that's the case, if gravity is the only long-range force, then every other force acting on an object besides gravity would have to be what kind? Contact. Okay, because forces are either contact or long range, and if gravity is the only long range, then everything else is going to have to be contact. And if there's a contact force, that means there's something touching it that's exerting that force. Newton's first law. Object in motion will remain in motion at constant velocity unless acted upon by an unbalanced force. I'm assuming this is review that you've heard of this before. Okay? So this first law, objects in motion remain in motion unless acted on by an unbalanced force. What we get, what this really means, is that if an object has constant velocity, then we know all the forces acting on it have to be balanced. And similarly, if an object has balanced forces, we know that it must have constant velocity. Okay? Think back to our dune buggy experiment. What kind of velocity did the dune buggy have? Constant velocity. What can we conclude about the forces acting on the dune buggy? They had to be balanced because it had constant velocity. That's what Newton's first law says. So what does it mean to have balanced forces? It's one thing to say, oh yeah, the forces have to be balanced, but what does that actually mean? Well, balanced forces means that the up forces equal the down forces, and the left forces equal the right forces. In other words, if you look at all of the forces acting on an object, you take all of the ups added together, they will equal all of the downs added together. All of the lefts equal all of the rights. That's what it means by balanced forces. And we'll look at a couple of examples here in just a minute. So up equals down and left equals right. Force diagrams are a way to draw a picture or an illustration or a representation of the forces that are acting on an object or a system of objects. And they're pretty simple to do, just a few basic steps. The first thing we do is we identify the object or objects we wish to analyze. This is our system. We draw a dot to represent the system. For example, if I want to look at the forces acting on my stapler, what's my system? The stapler. Yeah, it's the stapler. And so I would draw a dot to represent my system. I would then identify any long-range forces acting on the system, which for our purposes, that's going to be just the force of gravity. What direction is the force of gravity? Down. Yeah, pretty easy. Always going to be that same direction. After we identify long-range forces, we then identify any contact forces acting on the system, remembering that normal force is perpendicular to a surface and friction is parallel to a surface. We then represent those forces as arrows in the proper direction with the arrow length representing the magnitude of the force. What does magnitude mean? How strong it is. It's the size, the amount of force. That's what magnitude is. So a lot of force, going to have a long arrow. Just a little bit of force, a short arrow. So let's look at an example. Here we have a box on a table. The object lies motionless. So what's the first thing we do? The system would be, how do we represent the system? With a dot. So we draw a dot to represent our system. What's the next thing we do? We go with long-range forces, which means just gravity. What direction is gravity? So I do a downward arrow. I label it FG. Okay, arrow with label. Now, is the object accelerating? No. What do I know about the forces? It's got to be balanced, right? Because it's not accelerating. So the forces have to be balanced. So if there's gravity down, there must be something pushing up to balance it, right? And what's touching our box? The table touches the box. What kind of force can the table exert on a box? Up happens to be perpendicular to the surface, what do we call that force? That's a normal force. So there's an upward normal force, okay? So here we have the dot representing the system, arrows representing the forces. Any questions? Let's look at another example. Here I have a box suspended from the ceiling by 2 strings. What's the first step? So I'm looking at the box. How do I represent it? So there's my box there. Okay, next. Long range, which means gravity. What direction is gravity? Down. Draw the arrow, label it. And then? What's touching my box? The strings. What kind of forces do strings exert? Tension forces. What direction are the tension forces? In the direction of the strings. So I have 2 tension forces because there are 2 strings. Question?
So in the tension force, or whatever it's called, does it count if it's like a chain also?
Chain, rope, cable, string, that's tension. Yep. Okay. Now, is my box accelerating? What does that tell me about my forces? They are balanced. This is interesting. Does balanced mean that they're all equal? No. Let's take a look at this. So if I look at this, the force of gravity does not look like it's the same size as the tension, right? What does balanced mean? That up equals down and that left equals right. So if I look at that tension force, let's just pick this left one here, I could describe that direction as being partly to the left and partly up, right? And this right tension, partly to the right and partly up. If I take the part of each of those tensions that is up, and I put them together, they equal the down. And then if I take the amount of this that's to the left, it will equal the amount of this one that is to the right. That's what we mean by balanced. That the ups equal the downs and the lefts equal the rights. That does not mean that all of the forces are equal. Okay? Any question about that? Let's do another example. Here I have a block at rest on a ramp. What's the first thing I do? Do a dot to represent my system, which is my box. In this case, just for ease and convenience, I'm drawing a shadow of the ramp itself. At the end, I'm going to take that away so we can see what the diagram would look like. But for now, just for the direction part, I'm putting it there to help us see what direction these forces are. What's the first force I always draw? Gravity, what direction is it? Straight down. Okay, it doesn't matter if I'm on a ramp, gravity still pulls straight down. What do I do next? I need to find my contact forces, right? What's touching my box? The ramp. What kind of force or forces can the ramp exert? Friction and normal. Okay, I'm not going to do tension because there's no strings, but a surface, like a ramp surface, can possibly exert friction force and normal force. What direction would the normal force be? Normal is going to be perpendicular to the surface. So it's going to be kind of at that angle like that, so that it's a 90-degree angle to the surface. And friction is what direction? Parallel to the surface and resisting motion. If there were no friction, what direction would the box move? Downhill. Friction is going to oppose that, so friction must be uphill. Okay? Any questions about this? Now, how can I tell if this is balanced? So I'm going to look at these forces because that friction looks pretty small. Okay? So I'm going to look at these forces. I'm going to see there's this teeny little bit of friction. This part that's up, I'm going to take this part of the normal force that's up, and if I combine them together, the up equals the down. The amount of friction that is to the left equals the amount of normal force that is to the right. And so they are balanced. Is there any question? Next time, we're going to learn a little bit about how to split these up, the forces when they're at angles, how to split them up into the horizontal and the vertical parts. But for today, we're just going to practice drawing these force diagrams.